One use of differentials is in error propagation, and here's the idea. If a measurement is made of some quantity, the measurement will not be exact. The measurement won't be exact. So in other words, there'll be some sort of error in the measurement. Okay? As this measurement enters into a computation, the question is, will the computation tend to magnify the error or tend to diminish it? And this concept is called error propagation. All right, how does the error get propagated through a computation? So let's consider this example. One side of a right triangle, pretend one side of a right triangle is known somehow to be exactly 25 centimeters. All right, the opposite angle of this triangle, of this right triangle, is 60 degrees, with a possible error of plus or minus 1 degree in the measurement of that angle. Let's use differentials to estimate the error when the adjacent side is computed. So let's make a little drawing of this situation. Okay, so we have a right triangle. And this side is known to be 25 centimeters. Okay, exactly somehow. Let's call this side A as the adjacent side, and that's not known exactly. And theta, the angle, and that's not known exactly. It's around 60 degrees, but it's not known precisely because it's been measured. Okay, so let's see, how would we calculate this? Well, we know that tangent of theta is equal to 25 centimeters, the opposite side, over A, the adjacent side. If I would multiply both sides by A, I would get A times tangent of theta is equal to 25 centimeters. And then if I multiply both sides by the reciprocal of tangent, which is cotangent, I would see that A is equal to 25 centimeters times the cotangent of theta. Okay, so what we want to do is we want to estimate the error in A, which the error in A we'll call delta A. Okay, and delta A can be approximated by the differential dA, and this differential is given by the derivative of A. In this case, A depends on the variable theta, so with respect to theta times, d theta. And a mnemonic, of course, is that if you think of the thetas as canceling out, you'd find that out. So let's calculate the derivative of A. The derivative of A is going to be 25 centimeters times the derivative of cotangent of theta with respect to theta. The derivative of cotangent is negative cosecant squared. So this would be negative 25 centimeters times cosecant squared of theta, and then times d theta. All right. Okay, now let's fill in the blanks. Well, if theta is 60 degrees, and I'll just draw a new triangle so I don't clutter up the original. All right, then the sides, this side is going to be the short leg of the right triangle, and the sides are in the proportion. 1 is the short leg, 2 is the hypotenuse, square root of 3 is the long leg of the right triangle. So let's see, so cosecant, all right, is reciprocal sine. Sine is opposite over hypotenuse. So cosecant will be hypotenuse over opposite. So this will be negative 25 centimeters times 2, the hypotenuse, over square root of 3, the opposite, but we have cosecant squared, so this will be squared. And then d theta is 1 degree, but remember that when we're dealing with angles like this, we need to express them in terms of radian. So 180 degrees is the same as pi radians, so we could write 1 degree as, and of course this could vary in either direction, plus or minus pi over 180. And so now let's do these computations and see what we have. All right, we'll have negative 25 centimeters. When we square 2 over the square root of 3, we get 4 over 3, so times 4 over 3 times this plus or minus pi over 180. If this pi over 180 is positive, this whole quantity will be negative, and if it's negative on the bottom, this whole quantity will be positive. So since positive is on the top here, all right, that would make the quantity negative. We'll put the negative on the top, and since negative is on the bottom, that would make the quantity positive. We'll put positive on the bottom. So it would be negative or positive 25 centimeters times 4/3 times pi over 180, and I've computed that. That turns out to be approximately minus or plus 0.5818, and that of course would be in centimeters. So the error is about 1/2 of a centimeter, which would be roughly, this would be an estimate. Now the question is that a good error or a bad error for this computation? Is that good or bad? Well, it would depend on the size of the adjacent side. If the adjacent side were 200 centimeters, well, 1/2 a centimeter would seem pretty good. On the other hand, if the adjacent side were 3 centimeters, then an error of 1/2 a centimeter would be kind of a big error. So if we want to judge this error, whether it's good or bad, this is, and by the way, maybe I should give this a name, this is called the absolute error. So we've just estimated the absolute error. All right. If we want to judge whether this absolute error is good or bad, we look at an idea called the percentage error, which is related to the relative error. Okay, I just have those computations here for you to look at if you need to. And the percentage error, well, it's related to the relative error. And remember, the absolute error was delta A. To calculate the relative error, you'd take the absolute error in A and divide it by A itself. This will give us the relative error. If I express this relative error as a percentage, that would give us the percentage error. So this is going to be, of course, all right, the absolute error would be approximately the differential. And since we have the absolute error divided by A, this will be approximately the differential divided by A. Now remember that the differential was the instantaneous rate of change in A with respect to theta, and then times d theta. So we'll have that over A. All right, let's recall that A was 25 centimeters times the cotangent of theta, and that the derivative of A with respect to theta was negative 25 centimeters times cosecant squared of theta. And so we'll have here then, all right, negative 25 centimeters cosecant squared of theta times d theta, all over, excuse me, A, which was 25 centimeters, times the cotangent of theta. Let's see, notice that the 25 centimeters cancel, and so I'm left with just the opposite of the cosecant squared of theta over the cotangent of theta times d theta. And you could use some trig identities, but let's recall our right triangle. Remember that theta was approximately 60 degrees, and so the ratios of the sides are 1, 2 for the hypotenuse, square root of 3 for the opposite side. And let's see, cosecant was the hypotenuse over the opposite, so this would be negative 2 over the square root of 3, and we have cosecant squared again, so that would be squared, over cotangent is the adjacent over the hypotenuse, or I'm sorry, the adjacent over the opposite, which would be 1 over the square root of 3. And then times d theta, well, d theta was plus or minus 1 degree, and we had to express that in radians, so plus or minus pi over 180. Okay. All right, so let's take a look at this. If we look at this, we'll have a negative or positive, again, just like before. When this is positive, this whole quantity will be negative. When this is negative on the bottom, this whole quantity will be positive. And we'll have 2 squared over square root of 3 squared, so that'll be 4 thirds times, multiply by the reciprocal, square root of 3 over 1 times pi over 180. And if I would multiply that out, that would become approximately 0.0403. You can check that on your calculators. And so this would be the relative error, would be approximately 4/100ths. So the percentage error would be approximately, and maybe I better label this relative error. To come up with a percentage error, we just express this as a percentage, and it would be minus or plus 4.03%, and this would be the percentage error. Okay. All right, so that's an idea. We'll do another example of error propagation in the next video.